In this screencast, I will demonstrate how to define and check safety performance indicators, called SPIs, using FASTEN. This screencast has three parts. At first, I will briefly introduce the SPIs for people who are not familiar with it. Then, I am presenting at a glance the process, which involves the verification and validation of the safety case. And thirdly, I will give a brief tool demo about how SPIs are supported in FASTEN. Let me briefly start with a brief introduction to SPIs as defined in the UL 4600 standard for autonomous systems. SPIs are defined as follows. An SPI is a metric supported by evidence that uses a threshold comparison to condition a claim in a safety case. Let us take a look at a toy example safety case about an UAV. The top claim is that the system is acceptably safe to operate. This claim is developed into subclaims, and we will have, at some point in the structured assurance case, branches about the sufficient performance of the perception and the trajectory planning systems. The claim about the perception could be, for example, developed along different sensor modalities, and at some point could contain a claim about the performance of the camera. Let us have a look now at potential SPIs associated to this safety argument fragment. Associated to the top-level claim, we could define an SPI which considers the number of accidents per 1 million of traveled miles, and another SPI which considers the number of incidents per 1 million of traveled miles. Associated to the claim about the performance of the perception subsystem, we could define an SPI which considers the number of missed identification of vulnerable road users per million of traveled miles. Associated to the claim about the trajectory planning, we could define a SPI which considers the number of activations of the emergency braking function per million of traveled miles. Going towards the lower levels of the safety case, we can define SPI for the performance of the camera, such as the inconsistent classification of objects exceed a certain threshold per million of traveled miles, and an SPI about keeping safe distance to vulnerable road users. The SPIs associated to the higher level claims are called lagging SPIs. They tell us about bad things which have already happened. The SPIs associated to the lower level claims are called leading SPIs, and they should have a prediction power about bad things which will happen in the future. To sum up, an SPI is an under-approximation of the negation of a claim. If a certain SPI is violated, then the associated claim from the safety case is invalidated. A claim can, however, be invalidated even if all SPIs associated with it are inactive. SPIs can be used to continuously check the validity of the safety case based on concrete data gathered from the system during operations. This brings us to the need for continuously checking the safety case both during development phase, continuous integration/verification, as well as post-deployment, continuous validation based on operational experience. Continuous verification and validation is performed not only at system level, but also at subsystem or component levels. Looking now at a bigger picture, in the continuous development operations setting, we have, besides the source code itself, also other artifacts like the design or safety case which need to be continuously verified. Once a new release happens, it is deployed on a fleet of autonomous systems, and data is collected and saved in a database. This field data is put in correspondence to the safety case, for example with the help of SPIs, and used to validate the safety claims, top claims, intermediate ones or lower-level claims, based on concrete experience gathered during operations. From a workflow perspective, we can distinguish several stages. Firstly, the data is collected from the fleet in form of raw data. This raw data is curated and aggregated in a subsequent step. And finally, this curated data is used as inputs for the SPIs-based checks of the validity of the safety case. In a previous screencast, we demonstrated the development phase verification of the safety case using FASTEN. As an example in FASTEN, we created a mini project about a drone, which helps emergency responders such as firefighters when they are in action. This project contains a set of system requirements, a specification for operational design domain where the drone will be active, a sketch of hazard analysis using STPA, an example architecture description, and a safety case model using the GSN language. In this screencast, we focus on the runtime verification phase using SPIs. The operational design domain is defined as restrictions of concepts and potential values based on a world model with various dimensions arranged in a taxonomy. Let us consider that the curated and aggregated data about incidents is available as a comma-separated values file with columns ODD dimension, dimension value, total exposure of the system in this ODD value, incident type, and number of incidents. For example, on the first line of this file with curated data, we have the data about the number of incidents in Germany when the system had 5,000 hours of exposure. Concretely, on the first column, we have the odd dimension country. On the second column, we have the value of the country dimension to be Germany. In the third column, we have the information that the system had 5,000 hours of exposure. In the fourth column, the type of incident is near collision. And in the fourth column, the number of incidents is 1. Similarly, another entry in the curated data is that in Sweden, we also had a near collision incident, but the exposure was 15,000 hours. And in the US, we had 3 near collision incidents in the 50,000 hours of exposure. We can have also other ODD dimensions, such as environment temperature, and other types of incidents like severe altitude loss, as illustrated on the fourth line. When the temperature was between 20 and 30 degrees Celsius, the number of severe altitude loss events is 5. On the next line, we have the information that in the 200 hours of exposure in medium precipitation, we had 1 severe altitude loss event. One of the argument legs claims that the changes in the operational design domain are monitored for increased risk of already defined hazards. Potential SPIs associated to this claim are that the dimensions collected from runtime are already known and consistent with the analyzed dimensions in the model. Another SPI is that in any new country where the system has an exposure below a given threshold, there are no recorded incidents. We specify these two SPIs in FASTEN using a dedicated language construct. In this language, an SPI has a name, a description about its intent, the logic specified as a code snippet, and 1 or more associated claims from the safety case. The description is given in a textual form and can reference other parts of the model. By pressing Ctrl plus mouse click, we navigate to the definition of the ODD. Each SPI references 1 or more entities from the safety case with which it is associated. We can navigate to these corresponding parts of the safety case by following the references. The logic which implements the check is written in Java. In our example, the checking logic reads the text file available as comma-separated values and checks the availability of ODD dimensions and the incidents in the case of low exposure. For running the checks, we firstly need to build the checking code and then run the model checker integrated in FASTEN in the same manner as if we were checking any other constraints. Our example produces 2 failures. One of the failures is related to the fact that the data collected from runtime, available in the CSV file, contains reference to the environment temperature. This, however, has not been defined in our ODD specification, and thereby we identify a contradiction between the actual data gathered from runtime and our design model. We can fix this by enhancing the ODD specification to consider the environment temperature as well. The consistency between the data gathered from runtime and the design model has been re-established, and thereby when we rerun the model checker, we get only 1 error. This error tells us that in Germany, we have only 5,000 hours of exposure, but have already registered a near collision incident. Addressing this violation would require much more analysis about the system design. This is out of our scope now. Let us commit our changes on the branch demo/spis_integration_live and push them to GitHub. The SPI's checks can be run also in a continuous manner with a workflow on GitHub. We trigger them manually by selecting the workflow and triggering it on our branch. In a few seconds, the workflow starts. Let us briefly look at the logs. We remark that one of the steps is downloading the runtime data available in another repository on GitHub. Let us briefly look at this repository containing the runtime data. The data is organized in folders and, as already mentioned, saved in textual files in the comma-separated values format. The design and assurance models are thereby in one repository, whereas the runtime data are in another repository. They are combined as part of the workflow for checking the SPIs. After a few minutes, the workflow ends, and we get the same model checker error that we got in the FASTEN IDE. In this screencast, I have briefly introduced the safety performance indicators used to check the validity of the safety case based on the data collected from the runtime. I have presented a high-level process about the collection and checking of an SPI and demonstrated how FASTEN supports the definition and automated checking of SPI both locally in the IDE as well as in a workflow ran automatically in the cloud as part of a continuous validation pipeline. Give this a try in your own workflow and see how it fits. Thank you for watching and see you in the next screencast.